Okay, hello everyone. My name is Jianxi San. I'm a graduate student of Purdue ECE. Today I would like to give a lecture on ROC curve and its analysis. Okay, so if you want to learn more about this lecture, or if you want to see other lectures on different topics, please visit the website here. Okay, so this lecture is organized as following sections. Firstly, I will give an introduction about ROC and ROC curve. Then a simple example is investigated to derive the idea of the ROC curve. In order to scientifically represent ROC curve, some statistics terms will be introduced in the definition section. So how to use ROC curve to analyze the classification process and how is the performance of the ROC curve will be given in the last section. Okay, so let me start with the introduction. So basically, what is the ROC curve? So ROC represents the receiver operating characteristics. And what is the ROC curve? That is the curve represents the relationship between the hit rate and the false detection rate. And how to use ROC curve. So the plot of ROC curve illustrates the performance of a binary classifier system as its discrimination threshold is varied. Okay, so let me start to introduce how to derive this ROC concept from a very simple example. So let's consider a diagnostic test for a disease. There are only two possible outcomes, which are positive and negative. A patient takes the test and gets either positive result or negative results. So we can assume the testing process as a classifier, and the disease-related trait of a patient is the input feature vector, and we pack them up as a multi-dimensional feature vector. Since the result go to either positive, which is green, or the negative, which is red. The testing process is basically a binary classifier system. Okay, so if we apply the general Bayes rule, which is used for classifier, in the classifier, G1 and G2 are the product of the density of each class and the class prior. A general discriminant function G of feature vector can be written as the difference between G1 and G2. By comparing the value of G with 0, we can choose class 1 or class 2 accordingly. And the threshold can be calculated by reversely solve the denomination function at the result 0. But here's the question. In practical, we don't know the class probability density. If we use Bayes rule, we have to find a way to estimate the density from the training data and calculate the threshold. We may ask the question again, is there any way to find out the threshold from training data without estimating the density? Actually, ROC curve came to rescue the world. So let us come back to our disease testing example and see how to derive this ROC method. To make things easier to demonstrate, we assume our feature vector is one-dimensional value. The red curve is the product of the negative class density and the negative class prior, while the blue curve is the product of positive class density and the positive prior. So let us look at what will happen when the threshold position is actually moving. The classification process chooses negative and the positive class based on the feature value is less or larger than the threshold. From the figure, we can see the threshold value will affect the performance of the classifier. Intuitively, you can think about that. There must be a threshold value that can optimize the classification accuracy. So in other words, there's only one option, optimize the threshold value that can optimize the performance of this classifier. Okay, before we introducing the way to find out the optimal threshold, let's look at some new terms that are used to represent the ROC curve. Okay, the first one is the blue area. Is the blue area here. So this area is classified as positive, and in reality it is indeed positive. So they are correctly classified. So we name this region as true positive. Okay, so the second region is the small red region here. So this region belongs to the negative curve, but it's classified as red. This is classified as blue. This is not correct. We name this region as false positive. Okay, so the third one is the big red region here. So this region is classified as negative, and they are indeed negative. This is correct, and we name it choose negative. The last term is the smaller blue region. This region is classified as negative, but in reality they belong to the positive curve. This is not correct, and we name it as false negative. So all possible classification results can be summarized in this table. For this two classes example, all the four possible results corresponds to 4 evaluations we just defined. Patients are diagnosed as normal or abnormal on the negative and the positive results from the testing classifier. Of course, some of the results we have from the classifier are not correct. Okay, so here are two statistic terms that we need to define. So the first is the sensitivity. Sensitivity is the ratio between the choose positive and the summation of the choose positive and the false negative. So if you look at the previous graph, with the two curves, this is the big blue area over the area under the blue positive curve. So that is the ratio of this area over the area of the area covered by the blue curve. In another word, sensitivity represents the number of the class positive data points classified as class positive over the total number of the class positive data points. So let me repeat that again. So the sensitive is basically the number of the class positive data points classified as positive class positive over the total number of the class positive data points. And this is accurate actually, so we name it as give another name, which is a hit rate. So the second term is the specificity. So specificity is the ratio between the true negative and the summation of the true negative and false positive. So if we go back to the curve again, this is just the big red area over the area covered by the red curve, which is the negative curve. It is also easy to see that 1 minus the specificity is the number of the class negative data points classified as class positive over the total number of the class negative data points. Because this is wrong classified, so I'll give another name to the result of 1 minus specificity as false detection rate. This graph demonstrates how the value of classification threshold will affect the area of the four regions we just defined, which are Tn, Fn, Fp, and Tp. Based on the observation, we can see that the heat rate and the false detection rate will correspondingly change as the threshold value changes. So the ROC analysis is the process of finding the optimal threshold by evaluating the result of the heat rate and the false detection rate as we change the threshold values. Okay, so let me show you the demonstration on how the value of the threshold will affect the heat rate and the false detection rate. So here's the general case of two classes with 1D feature vector. So the left figure is the class density multiply the class prior curve for each class. So the black one is class 1, the red one is the class 2. In order to demonstrate a general case, there is an overlap between the two curves. So the figure on the right is the heat rate versus the heat rate versus the false detection rate, which is the cold ROC curve actually. So when we place the threshold all the way to the left, and the two curves like is shown in the left figure, the corresponding points is around 1% for heat rate and almost 0% for false detection rate. So if you mark the point in the ROC curve, the point should be here. So if you increase the threshold toward right a little bit more, then the corresponding points on ROC curve is moving upward along the curve. So at this time, the point moved upward to here. If we move even more, the corresponding points is moving up even more. If we plot the point track on heat rate versus the false detection rate, we can generate this ROC curve. So let me show you this again, so it will give you a better idea to see how this ROC curve is constructed. So I start with the threshold on the left and I move it to the right. In the process, you see the ROC curve is constructed and the curve will looks like this. Okay, so this is the final ROC curve. From the curve, we can see that as the threshold increases, the heat rate is increasing, while the false detection rate is also increasing. But ideally, the best optimization is to find out the threshold that gives the left top corner where the heat rate is 100% while the false detection rate is 0%. That is the ideal case, but in reality, this cannot be achieved. So let's compare the performance of testing or our classifier. So again, in the ideal case, if the distribution of the two classes are not overlap at all, there is a threshold that can make a 100% heat rate and 0% false detection rate, just like the figure on this left shown. But if the distribution of the two classes, the curve, are overlapped completely, In other words, if the two curves are the same curve, the ROC curve will be a straight line with a slope of 1. So that is what is shown in the right hand side curve. So let's look at the regular ROC curve results. Okay, so these are the shape of the most ROC curve looks like. Okay, so most of the time the ROC curves connect the points from 0% and 0% to 100%, 100%. So, and the curve shape is a convex curve toward left top corner. So the evaluation of the performance of test depends on how close the curve to the left top corner. So the closer, the better. So from the figure shown here, so the left curve has shorter distance between the last top corner and the curve convex point. Obviously, on the right hand side, this curve has longer distance between the top left corner and the curve convex point. So as a result, we can conclude that the testing that generates the left curve is better than the testing generating the right curve. Okay, so this gives us a way to find the best threshold by looking at the point where you have the shortest distance. So that point, whatever the threshold that make that point happens, that should be your best threshold. So in this case, you avoid estimating the class density for each of the classes. So conclusion. So the ROC curve is used to illustrate the performance of a binary classifier system, as its discrimination threshold is varied. So, and it is useful when find the threshold without knowing the distribution of the two classes. Okay, that is pretty much what it is about the introduction about the ROC curve and how it is derived and how to use it to find out the threshold to identify the two classes without estimating the two classes distribution density. So here are the reference, and thank you very much. If you want to see more lecture, please visit the same website I mentioned in the beginning of this lecture. Thank you. You have a good day.